Hello and welcome to my semester final project, Python solution tutorial for civil engineering problems for my EGR 214 Numerical Methods for Engineers course at Cape Fear Community College, taught by Dr. Hans Chapman in the fall 2025 semester. This project was completed and presented by Jacob Whitby. So why do we use Python to solve engineering problems? It has several advantages. First is that it saves time. We do not have to analytically write out the solutions to the problems. It allows for repetition if you have changing variables in a problem, and it also reduces errors due to the fact that computers can round far further than we can count. And also for running simulations, again, if you have changing variables. So for problem number 1, we have a pinned fixed beam that has a load on it, and we have to determine what the maximum deflection is in the beam and where it's located at, and we are given the equation for deflection, and then we are given the variables that we are going to plug into it. Some relevant formulas we're going to be using are obviously the one that was given to us in the problem, and then the derivative of that, which we will get whenever we use the minimize scalar function in Python. And then we have the shear force, which is just the derivative of the moment, and then we have the moment equation as well. So in Python, I started out by importing NumPy and Pylab. This is going to help us plot it. First, I put in all the initial values that were given, and then I defined the function that was given also in the problem. And then we put in linspace from 0 to L, which is the full length of the bar, which is 400 centimeters. And then we had 100, because we have 100 different test points whenever we are going through and checking each point on this beam. And then we get this graph over here, which shows us that the maximum deflection is at about 168.61 centimeters from the pinned point of the beam, and then the magnitude of the deflection is about 0.33 repeating centimeters downward, and this is very helpful because now we know where actually in the beam is going to take the most stress, and so we can map out what points of the beam we are going to need to reinforce to make it suitable for the load. For problem number 2, it's pretty similar to problem number 1. We had a beam with a load on it, and we have the shear force equation here, 5 plus 0.25 x squared, and then V is the shear force and x is the distance along the beam. And we know, again from the last problem, that the shear force is the derivative of the moment, where the moment is the bending moment. And so that is the equation here to determine what the moment is. And so we are going to analytically integrate and then also use the composite trapezoidal and Simpson's rules to see how close the estimates are. Some relevant formulas for this problem are obviously the shear and moment equations that were given to us, and then also for the trapezoidal rule, we have the equation here, and then for the Simpson's rule on the right, this is just the standard analytical equation or formula that you would use. And in Python, I first imported NumPy, and then I defined the shear force function. And then I took the integration of that, and that gave me my moment. And then I printed the exact integration, and that showed us that the bending moment is actually 165.9166 repeating. So that's going to be what we base our trapezoidal and Simpson's rules off of. For the composite trapezoidal rule, I defined the trapezoidal function and imported it from the library, and then I gave us 100 subintervals to be as precise as we can, and the same thing for the h being the step size of 1. That just tries to make our answer as close to the actual integration as possible. If you wanted to, you could give it 1,000 subintervals, and that'll get you to a more accurate answer. And then we go through and plug in the given values in the problem, and then we define the shear force equation and print the composite trapezoidal rule, and that gives us the answer of 166.375, which is about 0.45 bigger than the actual integration, so it's not far off. And then for the composite Simpsons rule, we kind of do the same thing. I defined the composite Simpsons rule and then gave it the same step size of 1 to be similar to the previous trapezoidal rule. And then I printed that out, and I got the answer of 165.958333 repeating, and so that was closer to the exact integration. And that makes sense because the trapezoidal rule uses straight lines in order to determine the distance of a curve, and the Simpsons rule uses parabolas or curved lines to do that. So obviously we have a more accurate number, but whenever you are looking for an exact answer, you would just normally use the exact integration. So our conclusions: in problem 1, we were able to calculate the maximum deflection of the load and also where it was located, and we were able to graph that so we could visually see it. And then for problem 2, we analytically solved an integral in Python, and we also computed the composite trapezoidal and Simpsons rule and saw how close those estimates were and compared those also. And overall, we demonstrated root finding and numerical methods to efficiently solve engineering problems in Python, and understanding the expansion of Python and the possibilities that we can use in the daily workforce to make our lives easier. Thank you for watching, and I hope you enjoyed.